This time of year, some mention of the amount of moisture in the air is almost always part of a weather forecast, given that it's directly related to your level of comfort. Sometimes it's generic terms such as humidity or water vapor in the air, but frequently we mention a specific measure, the dew point. The amount of water vapor in the air is tied to human comfort because evaporation of sweat is the primary cooling mechanism for the body, and the more water vapor already in the air, the less efficiently that process works. We have quite a few ways to quantify atmospheric humidity. For example, the mixing ratio is the mass of water vapor in the air divided by the mass of the dry air, that is, all the other gases such as oxygen and nitrogen. Another measure is called the vapor pressure. It's simply the part of the total air pressure exerted by water vapor. On average, surface air pressure is around 1,000 millibars, and 1 of 100 air molecules is water vapor, so a typical vapor pressure is perhaps 10 millibars. Now, practically speaking, neither of these is particularly easy to measure, and that's where the dew point comes in. Dew point is conveniently measured in degrees. To understand it, let's start by assuming that a blob of air, say the air above your front lawn, has a certain temperature. Now imagine the air cools in place, as would typically happen after sunset. If the temperature falls enough, eventually dew will form on the grass as water vapor from the air condenses, and the temperature at which the dew forms is the dew point. In the air, the equivalent change would be from a clear sky to a cloudy sky. Now, if we repeat the experiment, but with more water vapor in the air to start with, then you wouldn't have to cool the air as much for the dew to form, which means the dew point would be higher. And so, as the amount of water vapor in the air increases, the dew point increases. Now, the relationship between the two is not linear. That is, it's not a straight line. Instead, it looks like this. Dew point in Fahrenheit on the horizontal axis. The amount of water vapor in the air in millibars is on the vertical axis. This is an exponential function. The higher the dew point, the steeper the increase in the corresponding amount of water vapor in the air. But as a first guess, in the range of dew points relevant to summer, if the dew point increases by 20 degrees Fahrenheit, the amount of water vapor in the air roughly doubles. As an example, let's say the dew point one day was 50, which would feel comfortable, but then it jumps to 70 the next day, which would border on oppressive. You go from those two values up to the curve, then over to the vertical axis. The amount of water vapor in the air would on this scale go from 13 to about 26, an approximate doubling. And by the way, the relationship that produces this curve, one that is well known to all our meteorology students, is called the Clausius-Clapeyron equation. Google it if you want the gory details. I suspect that humidity will be mentioned in the extended forecast, which is next.